What's up, guys? I'm going to go through the steps to solving a kinematics problem, and then I'll walk you through two examples. Go ahead and pause the video and write down these 7 steps in your notebook. Then we will take them and apply them to 2 scenarios. Keep in mind I have the kinematic gems that you copied down in class in the bottom right, A, B, and C. The goal here in any kinematic problem is to get 3 known variables so we can solve for any unknown. Get 3 known, solve for any unknown. So the first step is to read through a problem carefully, paying little to no attention to what we're trying to solve for. So over here on the right, I have a situation where a car starts from rest and reaches 60 miles per hour in 1.3 seconds. What is the acceleration of the car? So I have this car, it's at rest at t0, and it gets off to 60 miles per hour when it's over here. So it's still moving to the right, 60 miles per hour when it's at that point, but we don't know how far it went. Now, step 2, draw some rough sketches. I got that at different points. Sketch here when it started, sketch over here after 1.3 seconds. Choose a specific object. Well, I'm choosing my car. I start that. Choose a specific interval in time, which the object is undergoing some constant acceleration. So this is where I'm starting my timer, and this is where I am ending the timer. Choose a coordinate system. I'm calling everything going to the right positive, everything going to the left negative. The 6th step is to draw a table that looks something like this, where we can list out all of our variables, and on the right, whether we know them, and if we know them, what is the quantity. So I did that here. Got my variables on the left: displacement, initial velocity, final velocity, acceleration, and time. All I know is that it starts from rest, so initial velocity 0, that it moves to 27 meters per second as it accelerates, and it does so in 1.3 seconds. So my first goal is to figure out the acceleration of the car. I'm going to go to my kinematic equations, pick out one that involves everything that I know. So initial velocity, final velocity, and time, and involves acceleration because that's what I'm after. Lo and behold, the first one works out just fine. So I pull that over here. V equals V naught plus AT. You'll see that this is just the definition of acceleration rearranged. So now I flip T to the bottom, solve for A, and then I finally plug in my values to get an acceleration of 21 meters per second squared. That's all good and well. Now I ask myself the second question: how far did it go as it accelerated? Well, this is delta x that I'm looking for, and I can really use any equation at this point. So I'm using the second one, B, pull that over to the right. Delta x equals initial velocity times time plus 1/2 AT squared. Solving for this displacement. I know I start from rest, so this term goes away. I have 1/2 21 because I just solved for acceleration. I forgot to put it in my table. As I solve for information, I should put it in the table. Times 1.3 squared, and I get a time, or a displacement rather, of about 18 meters. So the car went 18 meters as it accelerated from rest to 60 miles per hour, and we would be done. 18 meters. So let's look over here at the tennis serve problem. Take a minute to marker back. Look over the problem that you have in front of you. Hopefully you have the CAPM problem set 2 problems in front of you. If you don't, just give me a minute to pull this up. Bam. This is the problem we're doing. So Venus Williams has recorded a serve of 130 miles per hour serve in 2007. She pushed the ball a distance of 0.1 meters, and we're looking for the acceleration and the time. So let's go through those steps. Okay. All right, so we read the problem carefully, and now we're making our sketch. I have the initial time when the ball first makes contact, then it moves the ball 0.1 meters, and finally the ball is released from the racket or leaves contact with the racket. Third step, choose a specific object. I am looking at the ball. I start it. Choose a specific interval of time. My time here, it starts when you make contact with the ball, and then the ball leaves contact. Coordinate system, I'm calling the right positive, the left negative, and now we move down to the table. What do I know and what am I looking for? Well, I know the displacement is 0.1 meters. I know that it starts at rest, and I know it's sped up to 58.1 meters per second, so I'm looking for acceleration in time. Now, you might be asking yourself, where did I get this 58.1 meters per second? Well, I had to take the 209 kilometers per hour and do a little dimensional analysis on it to get it into a standard unit of meters per second. Once I did that, I was able to look at my kinematic gems and decide, well, I'm looking for acceleration. I have final velocity, I have initial velocity, I have displacement. C will do just fine for finding acceleration. And here is the algebra. I rearranged the expression to solve for A, and I got A is equal to about 17,000 or 16,900 meters per second squared. Now I'm looking for time. I have all of my information now because I just solved for A, and I'm putting it in my table as I go. So now I can pick out any equation that I want because I have 4 pieces of information. I chose B. So delta x equals v naught times t plus 1/2 at squared. I know that I start from rest, so v naught is 0, so this term just drops right out. All I'm left with is delta x equals 1/2 at squared, where I know the displacement is 0.01 and acceleration is 16,900. And I got a time of about 3.44 milliseconds. That's the time that this tennis racket is in contact with the ball, accelerating it up to that 58.1 meters per second. Hey, Ashley, how we doing? Oh, she doesn't like to be on camera. All right, well, hope you learned something.